All right, folks, I think we can start on time. So welcome to the afternoon session. And we're starting with, is it both of you presenting? So Julian and Felipe talking about Dagger. So.
All right, so what we're going to talk about in this talk is all the cool new things that we've been developing in Dagger over the past year since JuliaCon 2024. So we've been putting together a lot of stuff, but we should acknowledge the people who've actually helped make this happen. Myself and Felipe, as well as the many people on this list and some not mentioned. You'll see their icons here. They will be listed on the slides in the top right corner for when someone contributed a certain feature or helped push something through. So real quick, what is Dagger? Maybe you've come to this session and you have no idea what Dagger is. That's okay. So Dagger is essentially a pure Julia runtime and scheduler, and essentially an implementation of automatic parallelism. And we're going to see some instances of that automatic parallelism in a little bit. Additionally, Dagger provides a number of abstractions for multi-threading, distributed computing, including with distributed.jl and MPI, and targets all of the GPUs available into the Julia ecosystem through these abstractions. Additionally, Dagger provides a built-in partitioned array called a D-array, and algorithms which run on top of these D-arrays in a highly parallel manner using these previously mentioned multi-threaded, distributed, multi-GPU capabilities. And additionally, there's a fancy framework that we have called DataDeps, which allows you to write these highly parallel algorithms if you need to write something that's not yet implemented.
So now that you know what Dagger is, what can it really do? Well, it's proposed to be, as Julian mentioned, an automatically parallel system. So if you want to use MPI, it should be as simple as declaring the acceleration. As you can see on the second line there, you just declare your GPU arrays as you would in a GPU implementation. And then you would set your options for running the following algorithm you're about to implement with options call. You distribute this array or this many arrays to one, many, or a cluster of GPUs. You do a really simple add stencil call with the macro you're seeing, and it works as a broadcast would in this example. However, you can build any stencil algorithm you want with padding, with wrapping, and your boundary conditions for a convolution.
And also, real quick, DA, DB, and DC in this example are D arrays that where the partitions live on multiple GPUs multiple MPI ranks simultaneously. And so the stencil up here is then running on multiple GPUs across multiple ranks. Just wanted to make that clear. So, okay. One of the key things that people have brought up again and again about Dagger is that there's a lot of overhead. Dagger has a lot of task overhead. Dagger makes a lot of allocations when you use it. And that has really impeded the performance of many calculations. So what we've done over the past year and a half is really try to push down Dagger's overhead into manageable levels. And so we were able to succeed at that. So through quite a lot of just hard software engineering work and improving type stability, memoization, caching, all sorts of tricks, we were able to get Dagger's overhead down by about 2 to 4x for quite a lot of problems, especially for where the problem is dominated by task overhead, where you're working with lots of very small elements, and thus having many tasks. So in this example of doing a matrix multiply, we went from 5.3 seconds on the prior Dagger master down to 1.6 seconds with quite a large drop in lock conflicts of almost 10 times. And this is now living on master on Dagger 0.19. So additionally, something that we've been working on is improving GPU support. So previously, anyone who's used Dagger with GPUs knows that we've had the Dagger GPU package. It was kind of annoying that we had to have Dagger GPU. It's like, why not just have Dagger and CUDA and you're done via package extensions? Well, that's what we did. So now if you want to use GPUs and Dagger together, you just say using Dagger, using CUDA, and you're done. All of the code that you need is loaded. We've also added a bunch of tests running with every single commit pushed to the Dagger repository that run across all of the supported GPU platforms, which for reference are CUDA, AMD GPU, one API, Metal, and OpenCL. And everything is going to be tested on all of these backends in the near future. Additionally, we have good tested support for linear algebra and for stencils that we're pushing through now, working out a few little details. And all of this should support multi-GPU as well. So taking a slightly different tact, there's quite a lot of applications that are best expressed as a continuous set of operations, or a set of operations being done on a continuous stream of data. So this is super common in the corporate world, using things like, not Hadoop, but all the various AWS services and stuff. People are, Kafka, that's the one I'm thinking of. Where you have just a stream of data coming in order, and you just want to run the same operation on this data again and again and again, potentially infinitely. So Dagger now has support for this, thanks to our Google Summer of Code project last year. We implemented a streaming interface where, in this example above, we're creating a channel, filling it with values, and then with just basically 3 actual lines, really 4 lines, we are taking values from a channel, adding 1 to each value, and then printing them. And that channel can be infinitely filled with values, and this will just keep running, no problem. 4 lines of code. Together with this work, as part of that same Google Summer of Code project, we also implemented something that's called cancellation. People often know this as like interrupts or Control-C. As kind of a related variant. And I have a talk about this tomorrow that goes into more depth, but basically what happens if your code is just running off the rails and you just want to stop it? Dagger now provides a mechanism called Dagger.cancel, which allows you to cancel or stop Dagger tasks and allow other Dagger tasks to take their place and run. And it also lets you, if you somehow manage to break the scheduler and you need to restart it, but you don't want to restart your Julia session, there's also a variant that lets you do that quite easily. I use this for development all the time. It works awesome.
So as Julian mentioned, we have the data depths capability. Integrated within that, with the framework we have in Dagger, we can quite easily enable, and we could do that, we could quite easily enable MPI, communication between tasks or between ranks, as you may know them in MPI. And you don't need to think about MPI whatsoever. You just build your data depths code as we showed in the first slide. You call a line, Dagger.accelerate bang, and you pass in the symbol of MPI. And all the collectives and P2P communication is done by us by default. We are developing a GSOC project with Jan, and he is developing the no-copy transfer of data between sparse arrays and dense arrays. So this is a performance improvement on our current MPI implementation, which we are almost ready to ship.
And there's a talk about this in actually a few minutes, 20 or 30 minutes in the same room about this topic. But so everybody here who has used distributed.jl knows that distributed.jl has various problems. For one thing, multi-threading support is not there. And that's kind of crazy when you want to be able to use Dagger with both multiple threads and distributed. You want to start, say, a Julia worker on each node, but then on each node you want to use multi-threading. Distributed.jl will just explode in spectacular ways if you try to do this. So what we've decided to do, now that there's this cool library called distributednext.jl, which fixes many of the issues that distributed.jl has, we have a very easy way to switch between distributed and distributed next, if you would like to be able to do those cool things. Again, see James talk in like 20 to 30 minutes about this. Something else that we're trying to do in the realm of just making things easier on users is parsing more things that users want to be able to express. So normally Dagger at spawn has been kind of rigid in what it supports, really just basic function calls, and that was restrictive for quite a lot of use cases. So what we decided to do is let's teach the parser to be able to handle these more complicated things, say, broadcast, do blocks, things like name tuple construction, get property, indexing, get index, set index, and all kinds of stuff that you can see here on the screen. We're also taking a look at the possibility of implementing support for generators or list comprehensions, begin end, which if you've used threads.atspawn, this is what threads.atspawn does. It's just a big block of code. We want to be able to support that with @spawn. And potentially for loops, what would that look like? I don't know. This is something maybe we need to discuss.
So in an effort to make parallelism easier, we developed the stencil macro that I've just mentioned in the first slides also. And you basically can set your boundary conditions for a neighboring access via a wrap or a padding call, where you can pad with zeros, with ones, or any other number you want. And essentially what you're seeing on the screen right now is a very basic convolution that works distributed on many GPUs and multi-node, and it can work with MPI with the features that were just mentioned. So the main goal here is to provide a very common operation in HPC, which is stencils and even convolutions, through a simple macro. You just call the data depths, spawn data depths, you see in line 7 right here, and then from that, the stencil is performed right out of the box.
All right, so Python integration. Maybe you could tell what I was going to talk about just from reading the title. So many people have expressed interest both within the Julia community and outside the Julia community about having closer integration between Julia and Python and other languages. And there's no reason that being able to access libraries like Dagger should be difficult from other languages. We should make this easy for users who really just want easy parallelism. So what we've done over the past year is putting together a very simple package, or very simple library in Python called Dagger.jl. And what this basically provides is just a very simple set of bindings to Julia through the Python call interface, which allows you to do things like spawn Dagger tasks, fetch the result, and wait on these tasks. Now, this is very basic. You can build things with this, but obviously there's quite a lot more in Dagger that we want to expose. D-arrays, data depths, really the whole thing. So this is very much work in progress. If anyone's interested in cross-language integration, please reach out. And it's not just limited to Python. We're also looking at integration with C++, R, MATLAB, whatever seems interesting to people.
Now with the bunch of computer science features you just saw, we wanted to also provide numerical linear algebra researchers, or basically anyone who wants to perform numerical linear algebra operations, with the opportunity of doing so in a performant way. And if you ever venture in the wonderful world of numerical linear algebra, you may know that you should want data or specific blocks of data inside a matrix to reside in specific parts of your computer. So that would integrate with the fancy parallel algorithms you were using by tiling, basically. And we've managed to provide that inside Dagger when you basically create a D array. So the calls you're seeing there, you're basically doing a 1,000 by 1,000 matrix with that specific tiling called in blocks, and you're assigning it with the well-known data distributions. So block cyclic, block row, or cyclic row, or any other common distribution you would want. We do support just 2D distributions. There's work to be done for 2.5D and 3D distributions, which are the fancier ones. So help wanted in this also. And as I've mentioned, if you want to implement these fancy parallel algorithms, you also want the underlying kernels you would call for each of these algorithms. And currently, due to the linearalgebra.jl package being tied to the BLAS/LAPACK implementations, we were not able to find it, or we were not able to build JLLs that would be easy to use, basically. So Rabab had this wonderful idea, which is the icon you see that is not me in the screen, to create a new package with pure Julian implementations of all the operations we needed in 2 kernels. So they are native linear algebra kernels. Where it's needed, we do offer kernel abstraction support, and we do implement the fancier kernel. So TS or TT, which is triangle on top of square, or triangle on top of triangle, which is needed for these intricate parallel linear algebra algorithms. And going to the main slide for linear algebra is we are implementing also the parallel algorithms for it. We currently have the matrix multiply, the non-pivoting LU, both the LU with row pivoting and the QR or the CAQR algorithms are being implemented, are almost ready to be launched. Matrix inverse, linear solve, and SVDs are future work to be done, and they are pretty performant, I would say. And they also work for MPI and for multi-GPUs and any other architecture you will have.
Go ahead, sorry.
And last but not least, we do provide we call this the fastest Fourier transform of the moment, just based on the FFTW. However, it's just a way of calling it like the Dagger-powered 1D, 2D, and 3D stencils we have. And we have support for slab or pencil stencils, which are basically a plane or a deep row into a 3D matrix or a tensor. And they work well with the common GPUs, CUDA or ROCm. And they were tested to work with MPI. So it's still work in progress. We still want help. It was basically an effort made by Senna, who is also here. And that's it, I think.
Yep. Because I know we're a little bit early on time, I just want to say that this work is still, all of this work is still ongoing. There is a lot of availability right now. We have the framework, basically, that we need for writing highly parallel algorithms in pure Julia. What we need right now are people who actually want to write those algorithms. So, you know, we've got the FFT, we've got some linear algebra operations, we've got this and that, and these are the basics, and most of these are implemented in about 10 lines of code. I mean, it's literally that simple. Our Cholesky algorithm is like 15 lines. And it's the kind of thing that is able to beat OpenBLAS in many settings. So what we really need right now, though, are more people who are interested in writing these kinds of highly parallel algorithms for their specific domains. You know, these algorithms do not cover everything that people want to be able to do. Even this FFT is really just the basic FFT call on, you know, a 1D, 2D, or 3D input matrix, and that does not cover a lot of cases. So what what I'd really ask is if anyone out there is interested in just giving this a try and writing an algorithm in Dagger, in DataDeps for their application to be able to really speed up your application code, please reach out. We can provide guidance on how to write these algorithms. It's really quite straightforward. And we'd love, if you're interested in contributing those algorithms to Dagger, we'd love to have them. So yeah, please reach out on Slack or just come find us here. And thank you.
Is there any overlap between what's going on in Nextla.jl and accelerated kernels?
Yes, so the answer is technically no right now. So just for background, accelerated kernels provides essentially GPU-capable algorithms that are for essentially like your basics. So MapReduce, sorting, things like that. NextLA is targeting more linear algebra specifically. Our goal with NextLA is to target GPUs for nearly all algorithms, and it may make sense for us to actually use accelerated kernels to implement those algorithms. And I mean, if accelerated kernels wanted that code into its core to be provided to everyone, that might be a possibility. But they're, not to use this word, but it's synergistic. They, you know, one provides the basics, one provides a linear algebra, and we would hope that also for other domains, people are going to do kind of the same thing we're doing with NextLA. But yeah, we're really focusing on linear algebra because we actually need those. For example, for Felipe's communication avoiding QR algorithm, there's quite a lot of algorithms that we do not have written in Julia in an accessible place, such as linear algebra.jl, they're just not there, that we need to implement this. Additionally, for algorithms like the SVD, we do not have the algorithms we need. And so this is an effort to really push forward and get those algorithms implemented in Julia so we can start making progress on the bigger algorithms that everybody really relies on.
I just have a quick question here. So what is the foundation that you built this on? I mean, I'm a little naive on some of this, but is this kind of like channels for the parallelism, or do you just kind of like make your own thing, or is this writing on another like aspect of what Julia already supports for parallelism?
Yeah, so this is, that's a great question. So the foundation of Dagger is everything flows through a unified task model, and that task model is built on top of things that you are familiar with if you've used Julia for a while, which are Julia's built-in multi-threading support. We just use threads.atSpawn essentially, distributed.jl or distributed next.jl. We call out to the GPU libraries for GPU support. It's basically a multiple dispatch trick. Dagger just moves the data to the GPU. It calls QArray or RockArray or whatever it needs to do, and then it just calls basically the same operation, expecting Julia to then do the dispatch to a GPU-capable algorithm. So we really try to build on top of the things that are already in Julia. And you mentioned channels, so our streaming support is built not on channels, but on somewhat on remote channels, but also some custom implemented logic for performance. We have a ring buffer implementation that we use for buffers, and there's stuff like that, but effectively there's just a remote channel between nodes. And so in that case, that is kind of closer to using channels. But yeah, for the most part, multi-threading, distributed.jl or distributed next, and then the GPU backends are what we use.
And it supports communication between the multiple threads? So if you have recursive routines or things that rely on each other that you still want to parallel, they can talk and get their values back and forth?
Are you saying like nested multi-threading where you call like a Dagger algorithm and then one of those inner operations is multi-threaded?
Right.
That does work. You may not always get the best performance, especially if we're talking about BLOS, because BLOS has its kind of its own threads and they compete with Dagger. This is a problem not just for Dagger, but also for other libraries which do multi-threading and then call BLOS. But for like a threads.at threads loop should work fine.
Okay.
Yeah, there may be some considerations there. You may want to rewrite some of it to use all Dagger for everything, but it should still work fine with good performance.
Okay,
Just,
excellent.
Yeah.
So I'm also have recently just started getting back into the multi-HPC GPU game. There's the Vulkan library. Is that supported as a backend?
Vulkan, you said?
Yeah.
Not yet, but if you're interested, we can make that happen.
Okay.
This is also maybe an appeal to the audience. In addition to algorithms, what would really help us in the data centers if people start to contribute applications. It could be small applications, it could be big applications, but it is much easier for me to make my case to my supervisors that we need more staff to help Julian et al. If there are users who, are sending, and you can do just send tickets saying this doesn't work, right? But like tell your HPC centers, here's an application, it's built on Dagger, it's built on other Julia technology, it doesn't work, or it doesn't work like I needed to, and that will actually help us get the resources. And in that context, I'm actually also wondering, Dagger is approaching, especially with streaming, it's looking like almost like a workflow manager. So have you started thinking about AI and integration of like, multi-application workflows using Dagger?
You're talking about, I'm a little bit confused about the AI part of that, but are you referencing like AIDA, like those kind of workflow managers?
The things that we are predicting that will be a pain to implement properly, and so users will probably do horrible things like, I'm going to use the file system to mediate how things work together, here's my modeling and simulation code, and here's an AI code, and I want my AI to like build a surrogate model for like some part of that simulation. So what you ideally want is something where you're doing some mod sim, and then you can call out to an AI to do some, I don't know, surrogate modeling or some training, and you don't want to go through the file system or, do horrible things.
Right. You essentially want data transfer and synchronization not happening through the file system, because on supercomputers and other HPCs, that's absolutely a mess, performance-wise especially. Yeah, I mean, that is definitely something that we're interested in. There is a Dagger-powered workflow manager called Waluigi.jl that was put together, and that seemed to work pretty well, but development hasn't really taken off at all. We are interested in this. There are a lot of opportunities. Streaming is one of those features that could benefit from this or could work well with this in certain cases, like high energy physics, for example. But I would say even just the basic task model would probably work well for the case that you're describing. We should probably talk more about like what applications look like and what their needs are to kind of figure out what would be the best API, and is there anything missing that we need to implement.
Okay, I also have a question. On the fourth slide, you allocated CUDA arrays and then called distribute on them. If you use that pattern, are you limited to arrays that must fit on a single GPU, and does Dagger also then have to duplicate the data to send it to all the workers that you have, or different devices that you have available?
That's actually a good question. Basically, when we did this example, we tried to show like, okay, this is one way of doing it. But if you declare it through Dagger directly, the short answer is no. Like, you don't need to have data that fits into one GPU. In this specific example, there is more for like teaching purposes, yes. Generally, no, because generally you wouldn't declare it as it's declared right now. You would call directly into the Dagger interface, and it would distribute it by default.
Thank you.
And, oh, sorry, go ahead. I was also going to add that we are towards the multi-GPU and the, considering GPU VRAM front, which we both obviously have to deal with. We are also taking a look at adding explicit memory awareness to Dagger's data depths so that even as we're distributing things across multiple GPUs, across multiple ranks or nodes, we are keeping track of how much VRAM is actually available. And if we're starting to exceed that amount, we will slow down certain operations or essentially pause certain tasks or just not launch tasks that will allocate more VRAM, or we can move data around within data depth. So we can move data wherever we want. We have full control. So in that case, we're definitely taking a look over the next year to improve that support greatly. So you could just work on massive data sets and not even care. It'll work fine.
And to further the point, this will also play out with the work stealing suite we're developing. So if a GPU starts to get filled, basically, and another GPU has the bandwidth to take the underlying work or data, it will steal that into basically chunks of the DAG. So,
Cool, thank you.
Let's thank the speakers one more time.